Hello, welcome to this video on solar panel partial shading, hotspots, and bypass diodes. When a leaf falls on a solar panel, it can cause the solar cell beneath it to be a local hotspot. I decided to explore this and some other aspects of solar panels. Many videos explain bypass diodes for solar panels using the case of a completely shaded solar cell. Some videos say that or show that partial shading of a solar cell heats it undesirably, but the videos don't generally explain how the heating comes about. I'm not an expert, but let's see how partial shading results in heating, and let's see how bypass diodes help. At the end of this video, you can think about half-cell solar panels. We will discuss a single solar panel. For multiple panel configurations, we will not really discuss AC microinverters versus DC power optimizers versus just a string inverter for multiple panels. Bypass diodes for each panel help in all configurations, though they are required for a string inverter configuration. The lecture script is available at a link given in the description of this video. Solar panels consist of many solar cells connected in series. More on this later. The solar cells are semiconductor p-n junction diodes or pin junction diodes, typically silicon, though not necessarily single crystal. Let's start with an ideal crystalline semiconductor p-n junction diode with no light absorption. Let's start with the voltage and current conventions for a conventional semiconductor p-n junction diode. In a bit, we will look at the solar cell convention, which is different. Diode voltage is taken to be positive when the p-type anode's contact is positive with respect to the n-type cathode's contact. If these terms are unfamiliar, don't worry about it or watch an appropriate video from Khan Academy. For an ideal semiconductor diode, the current is this exponential function of voltage divided by absolute temperature times a saturation current value for a particular diode. If you want to know how the semiconductor physics gives this function, that is available on videos from Khan Academy. Let's graph this current versus voltage for small values of voltage and current first. Here the voltage, the horizontal axis, ranges from negative 50 millivolts to positive 50 millivolts. At 0 volts, the current is 0. For positive voltage, the current into the p-type anode contact is positive. For an ordinary diode, this region, the upper right quadrant, is generally called forward bias. We'll cover solar cells in a bit. For negative voltages, the current with this convention is negative. The lower left quadrant is called reverse bias. This ordinary diode, not a photodiode, not a solar cell, only has operation in the upper right and lower left quadrants, where the sign of the current and voltage are the same in this convention for current. Power is current times voltage, paying attention to signs. Power is positive in the upper right and lower left quadrants. The diode is dissipating power at all non-zero voltages. The power is provided by a connected external circuit that results in the voltage. The dissipated power heats the diode. The amount of heating depends on the amount of power. A voltage and current in the lower right or upper left quadrant with this current convention would represent power generated by this diode and sourced into the external circuit. But this ordinary diode cannot generate power, and the IV curve does not exist in those quadrants. On this graph, the current levels are a fraction of a nanoampere and the power is a fraction of a nanowatt. But we will see that for a partially shaded solar cell, the dissipated power could potentially be tens of watts, which is undesirable. This scale is too small to be of interest for ordinary diodes or solar cells. Let's keep this function, this IV curve, but zoom out. First, let's zoom out the voltage to plus and minus 1 volt, but keep the current axis unchanged. If you've never seen this before, give this some thought before moving on. Visualizing exponential functions takes a little experience. For negative voltages, the current saturates. We won't care about the value of the saturation current in this video, but it factors into the calculations. Now, let's zoom out the current scale from nanoamperes to now amperes, about a factor of 100 billion. At this scale, the current is negligible except where the forward bias exceeds positive 0.5 volts. It is the same exponential as the prior graphs, but the change of scale changes how the curve appears. Now, let's introduce an important deviation from ideality: reverse breakdown. Let's include larger negative voltages. At large enough negative voltages, the diode will experience reverse breakdown, pass a lot of current, dissipate a lot of power, and heat up. For a solar cell, this reverse breakdown voltage may be in the range of -10 to -30 volts. It doesn't seem like solar cell specification sheets generally tell you their breakdown voltage. Reverse breakdown does not seem to be the reason why partially shaded solar cells get hot. Details of the breakdown current voltage relationship won't matter for this video, but the breakdown voltage impacts the discussion. The solar cell may also have some shunt resistance such that the reverse bias region current has some slope to it. This won't change the discussion in this video. Now let's look at solar cells. A photon of visible or ultraviolet sunlight gets absorbed in the junction depletion region and creates an electron-hole pair. The mobile carriers drift to their respective majority regions. Under the right circumstances, the solar cell supplies power to an external load, say 5 watts or more per solar cell in ideal conditions for modern solar panels. When a solar cell absorbs light, we get the I sub L current term on the right. This term is negative in the ordinary diode convention. The contact of the p-type anode is sourcing positive current into the external load. The solar cell is now a current source, not a passive element as the diode had been. Here is a family of IV curves for a single ideal solar cell under different solar illuminations. The horizontal axis is volts, the vertical axis is current in amperes. The black curve is for no illumination, the ordinary diode curve. The green curve is for 1,000 watts per square meter face-on solar illumination. The red through purple curves are for 200 through 800 watts per square meter. If these curves are totally new to you, there are good Khan Academy videos explaining the physics and electrical operation. In this video, I only want to add a few points that I think other videos don't cover. Now with illumination, there are currents and voltages in the lower right quadrant, which were not there with an ordinary diode. Power is current times voltage with attention to signs. In this lower right quadrant, the solar cell is generating power, sourcing it to a connected load. This is the desired quadrant for solar cell operation. For an ordinary diode, all positive voltages are called forward bias, though we only get appreciable current above half a volt. I don't know if terminology is different for solar cells, but some videos call the lower right quadrant reverse bias. This terminology will not matter for this video. Solar cells never operate in the upper right quadrant, with this convention for current. We will see later that solar cells are sometimes forced by load and partial shading to operate in the lower left quadrant, in which the solar cell dissipates power instead of sourcing it. Consider a solar cell with a current of -4 amperes and an imposed voltage of -20 volts, reverse bias. That solar cell will dissipate 80 watts, -4 amps times -20 volts, and heat up undesirably. We will see this. This happens in ordinary operation and does not require a reverse breakdown condition, though reverse breakdown will change the details. Cooling. Before we move on, let's think about the lower right quadrant and heating or cooling. The solar cell is absorbing sunlight, so its temperature will be hotter than for no sunlight. If the solar cell is connected to a load, then a fraction of the power absorbed from the sun gets delivered electrically to the load instead of adding to the heating of the solar cell. A reduction in heating of the solar cell, but not cooling, not air conditioning, not the Peltier effect. The solar cell is not cooler than ambient, but is cooler than a solar cell that is disconnected from a load and absorbing sunlight. Solar panel current convention. Because solar panels source power, their IV curves generally use the convention for current that current is positive when it exits the contact for the p-type anode. So, we negate the sign of the current of previous sections. So, for a solar cell, the current is positive light current minus the ordinary diode current. This is just the convention. It doesn't change the physics or electrical behavior, but now the quadrants have changed. With this convention and this graph, the solar cell sources power in the upper right quadrant, is never operated in the lower right quadrant, and will dissipate power, even considerable power, if the connected load and partial shading force the solar cell to operate in the upper left quadrant. Power delivered by the solar cell to a connected load is current times voltage. Current, voltage, and delivered power are positive in the upper right quadrant. In the upper left quadrant, current is positive, voltage is negative, and the power delivered by the solar cell to a connected load is negative, meaning that the solar cell forced into that quadrant is dissipating power. That power comes from the connected system, not sourcing power to the load. The green diamond at the right is the point on the green maximum illumination curve with zero current, open circuit, disconnected from the load. This is the maximum voltage for this curve in the upper right quadrant. 0.667 volts for this particular graph, but it varies for different solar cells and solar panels. Power is 0 because current is 0. The green square at the top is the point on the green maximum illumination curve with 0 voltage. Short circuit. This is the maximum current for this curve in the upper right quadrant. 10.6 amps for this particular graph, but it varies for different solar cells and solar panels. Power is 0 because voltage is 0. The point on the green maximum illumination curve that delivers the maximum power to an external load is the green dot at the upper right, the maximum power point for the maximum illumination curve. For my particular graph, this is 0.6 volts and 10 amps, supplying 6 watts to the external load. This varies for different solar cells and solar panels. Solar panel. Now let's switch to a solar panel, specifically 60 identical solar cells connected in series, such that their voltages add and the same value for current flows in all solar cells. Different solar panels have different numbers of solar cells. We will use 60 for concreteness. I show this as 3 strings, each of 20 cells, whose purpose I will explain later when we cover bypass diodes. The IV curve for this 60 solar cells in series, all receiving the same illumination, is just the single solar cell curve with voltage multiplied by 60. Normally, the spec sheet will show you only the upper right quadrant, but I suggest you also need to know what happens in the upper left quadrant to understand partially shaded solar cells, hotspots, and bypass diode operation. The green square at the top is the point on the green maximum illumination curve with 0 voltage, short circuit. This is the maximum current for this curve in the upper right quadrant, 10.6 amps for this particular graph, the same as for one solar cell. But it varies for different solar panels. Power is 0 because voltage is 0. The green diamond at the lower right is the point on the green maximum illumination curve with 0 current, open circuit, disconnected from the load. This is the maximum voltage for this curve in the upper right quadrant, 40 volts for this particular graph, 0.667 volts per cell times 60 cells. But it varies for different solar panels. Power is 0 because current is 0. The point on the green maximum illumination curve that delivers the maximum power to an external load is the green dot at the upper right, the maximum power point. For this particular graph, this is 36 volts and 10 amps, supplying 360 watts to the external load. This varies for different solar panels. The panel spec sheet will tell you the current and voltage at the maximum power point for the maximum illumination curve. Solar panel driving a load. At this maximum power point, 36 volts divided by 10 amps is 3.6 ohms. The black dotted line is the load line for a fixed 3.6 ohm load resistance. This simple picture will suffice for understanding partial shading, hotspots, and bypass diodes. If you already understand AC microinverters or DC power optimizers, you should be able to follow the following material with your understanding of your system, but it may be easier to understand the fixed load case first and I think you should understand this case. With the fixed load, each of the 3 strings of 20 solar cells is producing 12 volts at full illumination and 10 amps, 120 watts per string. All strings are producing 10 amps. This string is producing 12 volts. This string is producing 12 volts. This string is producing 12 volts. The total is 36 volts, which gives 10 amps in a 3.6 ohm load. Shading the entire panel. Now, suppose that a cloud reduces the illumination to 40%, 400 watts per square meter, for all the solar cells, the blue curve. For a fixed 3.6 ohm load resistance, the black dotted line, the solar panel will source at the blue dot. 4.24 amps, 15.3 volts, and 64.7 watts. In order to set up the case for a partially shaded solar cell, I want to stick with the fixed resistive load and not move to the right to the maximum power point for the blue curve, which a microinverter or DC power optimizer would do. We'll come back to that. Every solar cell is operating in the upper right quadrant of the panel IV curve, and there is no local heating when all the cells are shaded equally. The voltage on each of the strings is 5.1 volts. A partially shaded solar cell, reduced power, and a hotspot. Now, let's ask what happens if only one of the 60 solar cells is partially shaded to 40%, say by a leaf on the panel, and the others remain fully illuminated. This is a little tricky, and it leads to local heating and one motivation for bypass diodes. Here I'm showing the lower right solar cell as partially shaded to 40% illumination. That partially shaded solar cell now can source at most 4.24 amps. The 60 solar cells are in series, so they all source the same current, 4.24 amps. Assuming for now a fixed load resistance of 3.6 ohms, the voltage sourced by the solar panel must be 15.3 volts, as it was in the previous section, and the power sourced to the external load, 64.7 watts. The partially shaded solar cell has reduced the power output of the entire panel, as though all the solar cells were shaded, but they are not. Let's see what happens inside the solar panel. In order to match the 4.24 amps sourced by the partially shaded cell, the 59 fully illuminated cells will increase their voltage, trying to move from the green dot to the green X at the right. Each fully illuminated cell will source 0.65 volts at 4.24 amps, higher than the 0.6 volts for 10 amps. 59 cells will source 38.4 volts together. 4.24 amps and a fixed load resistance of 3.6 ohms gives 15.3 volts. The sum of the voltages on the 60 cells must equal 15.3 volts. .4 volts plus the voltage on the partially shaded solar cell equals 15.3 volts for this fixed load. So the voltage on the partially shaded solar cell equals 15.3 volts minus 38.4 volts equals minus 23.1 volts. The partially shaded solar cell gets forced into reversed bias in the upper left quadrant to match the voltage sourced by the solar panel current to this fixed load. The upper left quadrant is not shown on the solar panel specifications, but partially shaded solar cells can operate in that upper left quadrant when the panel is connected to a load, especially a fixed resistance. Still assuming a fixed load resistance of 3.6 ohms, with 4.24 amps and minus 23.1 volts reverse bias, the partially shaded solar cell is dissipating 98 watts. It is no longer sourcing power to the load, it is dissipating power. The power dissipated by the partially shaded solar cell is coming from the other 59 fully illuminated solar cells. The partially shaded solar cell gets heated by its power dissipation. It is a local hotspot due to partial shading, say from a leaf sitting on the panel. The hotspot could be seen by an infrared thermal imager. There are YouTube videos that show the thermal image. The other fully illuminated solar cells are not dissipating power or being heated by the flowing current. Only the partially shaded solar cell is a hotspot. The 59 fully illuminated solar cells are sourcing 162.8 watts. 64.7 watts to the load, plus 98 watts to the partially shaded cell. This is a surprisingly bad result. However, solar cells generally come with a partial fix independent of microinverters and DC power optimizers, which we will cover next, and then we will add in the microinverter. Note that the partially shaded cell is a hotspot only when the panel is connected to a load, not open circuit. There is local heating and loss of power for the solar panel when partial shading is 25 to 80% for a solar cell. Again, this is for partial shading of one or more solar cells, not the entire panel, under load. And it's a little different when you have a microinverter or a DC power optimizer. So far, we're talking about a fixed resistive load. Reverse breakdown voltage. We assumed that the solar cell was an ideal diode, infinite shunt resistance, and infinite breakdown voltage. A finite shunt resistance would slightly increase the current through the partially shaded solar cell as the voltage across it moved deeper into reverse bias. This would let a little more current flow through the panel to the load. If the reverse bias reaches the reverse breakdown voltage, additional current will flow. Current would increase. Assuming the reverse breakdown does not destroy or damage the solar cell, reverse breakdown would act as a voltage limiter by raising the current. I haven't calculated whether a reverse breakdown voltage of, say, 15 volts would lower or raise the power dissipation in the partially shaded solar cell versus, say, 30 volts. Perhaps you'd like to work it out. I did see one research article that created solar cells with low reverse breakdown voltage of a few volts to reduce the hotspot power dissipation. I don't know whether this will be a future direction for panel solar cells. Panel strings. Now, let's look at the voltages of the three strings in the panel during partial shading of one cell. The two strings that are fully illuminated but restricted to 4.24 amps will source 13 volts each, 26 volts together. The string with the partially shaded solar cell will have a voltage of minus 10.7 volts. We verify this for the 20 solar cells of that string. 0.65 volts times 19 minus 23.1 volts for the partially shaded solar cell equals minus 10.7 volts. So the two fully illuminated strings have plus 13 volts are generating plus 13 volts. But the string with the partial shading of one cell has minus 10.7 volts on it. Bypass diodes. The internet says that solar panels started coming with bypass diodes in the 1990s. Let's see how bypass diodes help this partial shading, power reduction, and hotspot situation. Later, we'll discuss the original motivation for the bypass diodes. This drawing shows, in red, three discrete bypass diodes, one per string of solar cells in the panel, installed by the panel manufacturer in the junction box at the back of the panel. The end user may not even realize these diodes exist. The installer does nothing to these bypass diodes. The cabling for the installer connects only to the outer two terminals. A solar system salesperson might not know about the bypass diodes. The bypass diodes are useful regardless of how panels are connected together. String inverter, microinverters, or DC power optimizers, as we shall see now. But beware, supposedly some panels do not come with bypass diodes. When all solar cells are fully illuminated, or all solar cells are illuminated equally, the voltage sourced by the solar cell strings is such that the three bypass diodes are in reverse bias, off, and do nothing. The bypass diodes are not solar cells. The bypass diode's reverse saturation currents are insignificant compared to the solar cell's currents. They don't reduce the solar output. The bypass diodes have higher breakdown voltage than the solar cell string sourced voltage, so they are just off in this normal operation. When forward biased, the bypass diodes can handle the rated current of the solar panel, so 10.6 amps for my example. The bypass diode should be reliable for the 30-year life of the solar panel. Now, let's look at that case of one solar cell being partially shaded with 40% illumination. Without the bypass diodes, the string on the right would have minus 10.7 volts if one cell was partially shaded, as we saw previously. With the bypass diodes, the bypass diode for that string would become forward biased, would conduct current in the forward direction, and would develop a small forward voltage. We will use 0.6 volts for concreteness. An ordinary silicon p-n junction diode, but the voltage may be a little higher at this current, or it could be lower for a Schottky diode. Let's call it 0.6 volts. The left and center strings are fully illuminated and would like to source 10 amps at 12 volts per string if this matched the load. Let's continue to use the 3.6 ohm fixed load. This is the IV curve for 40 solar cells, two strings of 20 each, fully illuminated. The operating point for a fixed 3.6 ohm load line is the green star. 25.5 volts, and 7.1 amps. This is a higher current than the blue dot without the bypass diode, 4.24 amps. Higher voltage and more power delivered to the load. 177 watts delivered to the load versus 64.7 watts without the bypass diode. The simple, negligible cost bypass diode more than doubled the power to the load in this example of a single, partially shaded solar cell. Here are the voltages on the strings in the panel. The rightmost bypass diode is on, forward biased, limiting the reverse bias of its string of 20 solar cells to minus 0.6 volts. The left and center string are each sourcing 90 watts for a total of 181 watts. The right string with its bypass diode is dissipating 4.2 watts. The load is dissipating 177 watts. 4.24 amps is flowing through that rightmost string with the single partially shaded solar cell. 7.1 amps minus 4.24 amps equals 2.86 amps. So 2.86 amps is flowing through that bypass diode, dissipating 1.7 watts. Let's look at the voltages on the partially shaded string. The voltage on each of the 19 fully illuminated solar cells that are constrained at 4.24 amps continues to be 0.65 volts. The bypass diode has reduced the reverse bias on the partially shaded solar cell from minus 23.1 volts to minus 13 volts. For this specific scenario of partial shading, if the reverse breakdown voltage of the solar cell is more than 13 volts, the bypass diode will be forward biased, on. If the reverse breakdown voltage of the solar cell is less than 13 volts, the operating point may be controlled by the breakdown voltage and the bypass diode may be off. It could be a little complicated. Let's assume the breakdown voltage is higher and the bypass diode is on. The bypass diode has reduced the power dissipation in the partially shaded solar cell from 98 watts to 55 watts, which reduces the local heating of the hotspot. The bypass diodes have more than doubled the power to the load in this example and nearly halved the undesirable hotspot power dissipation in the partially shaded cell. This is a great result at negligible increase in cost and negligible reduction in reliability. The bypass diodes only help the system, and their help is independent of whether multiple panels are connected to a string inverter, microinverters, or DC power optimizers. Let's calculate the power being sourced and dissipated. The partially shaded cell has reduced the power generated by the panel from 360 watts to 234 watts, but it would only have been 163 watts without the bypass diodes. 177 watts gets delivered to the load versus 64.7 watts without the bypass diodes. That 177 watts is all coming from the two unshaded strings. With the bypass diodes, the partially shaded solar cell dissipates 55 watts. Most of this power comes from the unshaded solar cells in that string in this example. The bypass diode dissipates 1.7 watts. So 177 watts delivered to the load, 55 watts dissipated in the shaded, partially shaded solar cell, 1.7 watts dissipated in the bypass diode, together make 234 watts dissipated, which is the power that is supplied by the 59 unshaded cells. You may want to pause and check all that math and your understanding before continuing. If one panel is connected to a microinverter or DC power optimizer, the active control element will shift the operating point, attempting to maximize power extraction. Here is the approximate IV curve for 59 solar cells at full illumination and one solar cell at 40% illumination, 3 bypass diodes, and solar cell reverse breakdown voltage more than 13 volts. At least I think this is the IV curve. I confess I find this confusing to think about, and I could have made mistakes. Do you agree that this is the IV curve? Where do you think the microinverter or DC power optimizer will operate in this case? Near the X? Near the triangle? Can you work out all the voltages? Is the bypass diode on or off? Is the partially shaded solar cell sourcing power or dissipating power, and about how much? If this interests you, pause the video and work out this case. Near that green triangle operating point, the global maximum power point for this case, the partially shaded solar cell would be dissipating power, and that string's bypass diode would be on. Near the green X mark operating point, a local maximum power point for this case, the partially shaded solar cell could be sourcing or dissipating a small amount of power, and that string's bypass diode would be off. But the bypass diode does no harm in this case. I don't have enough information to know how a particular microinverter or DC power optimizer will behave in this case. Let's look at a different related case. A completely shaded solar cell. Now, suppose that the partial shading of one solar cell proceeded to complete shade. Zero current in that cell. Without the bypass diodes, the current in all 60 solar cells in series would be zero, and zero power would be sourced. The microinverter or DC power optimizer cannot help when there is zero current in the strings in the panel. But with the bypass diodes, the string for the completely shaded solar cell is net reverse biased and gets bypassed, and the two illuminated strings continue to source power. This was the original motivation for the bypass diodes, to bypass a string that was not producing current. It's a little confusing to see how the reverse bias would develop. Imagine the partially shaded solar cell becomes a capacitor, the space charge layer, as it becomes fully shaded. Series current from the fully illuminated solar cells continues to flow, but now that current is charging the capacitor in the reverse bias direction. The reverse bias continues to grow until the bypass diode turns on. If there were no bypass diode, the reverse bias would grow until either reverse breakdown voltage is reached or all of the illuminated solar cells reach their open circuit voltage and current ceases. Now, suppose you have multiple solar panels connected in series to a string inverter with no microinverters or DC power optimizers. If an entire solar panel is completely shaded or all three strings have zero current, the active load of the string inverter should forward bias all three bypass diodes, and current should flow through the multiple solar panel system, even without microinverters and DC power optimizers. The string inverter system should source power if most of the panels are sourcing power. However, if different panels are partially shaded to different amounts, I would think that microinverters and DC power optimizers should deliver more power to the load than a simple string inverter. They will operate each panel near its maximum power point for the given illumination. Solar panels with half cells. Some solar panels implement half cells, with half the current and twice as many, in the following configuration, with bypass diodes. This diagram shows 120 half cells in 6 strings, series connection of 3 parallel pairs with 3 bypass diodes. I think I should leave it to you to analyze whether this design is an improvement under different shading conditions. If the bottom half of the panel, this half, is less illuminated than the top half, how does the half cell panel compare to the full cell panel? If the right third of the panel, here, is less illuminated than the left 2/3, how does the half cell panel compare to the full cell panel? If 1 or 2 adjacent half cells are partially shaded, how does the half cell panel compare to the full cell panel? Does it increase the power delivered to the load? Does it reduce the power dissipated in the partially shaded solar cell? Multiple panels. For a multiple panel system, use of per panel microinverters or DC power optimizers allows each panel's power generation to be optimized to its optimal power point in real time for its present illumination and shading. This is desirable, but adds to the cost and adds components that could fail eventually, fail on your roof. A cost-benefit analysis should include the labor cost of replacing potentially failed electronic units, for example on a roof, over the lifetime of the system. I hope this video has been useful to you. If I have made any mistakes, please leave a comment.